Okay, so here's another problem with equilibria involving this time Kp instead of Kc. And we're told in this problem that we've got iodine gas dissociating and forming iodine atoms. And Kp is pretty small, so that's telling us that there aren't many atoms at equilibrium, most of its molecules. And we're told that initially we've got 1 atmosphere of pressure of iodine gas and iodine atoms. And what we need to do is figure out what the pressure of both of those are at equilibrium. So we've got an ice chart problem clearly, but the question is, are we shifting from left to right or from right to left? And so we can probably answer that best by calculating Q, the reaction quotient. So we just have the partial of iodine atoms squared divided by the partial pressure of iodine molecules. And these are instantaneous. So the math here is pretty easy because all the pressures are 1 atmosphere, so that's basically 1 atmosphere squared over 1 atmosphere. And we probably don't even have to reach for a calculator here. We know that Q is going to be 1. So how does that compare? Well, Q is much bigger than K, about 3 orders of magnitude bigger. So that means that we're not at equilibrium. In fact, in order to reach equilibrium, Q has to go down. And since Q is basically products over reactants, we know that we've got to get rid of products and we've got to make reactants. And so what's that telling us? Well, here's our equilibrium. And we are shifting to the left-hand side. So that is, we're going to get rid of products at the expense of making reactants. So when we do our ice chart above, we can go ahead and we can shift away from the right towards the left. So let's go ahead and do that. So there's our reaction. And we can fill out our ice chart for it. And so initial change equilibrium. Now, up to now, the initial values we've been using concentrations. We could convert the pressure to concentrations if we wanted to, but it turns out that it's okay to use pressures here. Okay, why is it okay to use pressures? Well, let's move off to one side and have a quick look at the ideal gas law. We know PV equals nRT, so we can show that P equals N over V times RT, and pressure is equal to, well, N over V, that's basically just molar concentration, times by RT. So that's to say the partial pressure of any substance, X, is proportional to its molar concentration. It's also proportional to the number of moles. And so that means in our ice charts we can use either partial pressures, we can use molar concentrations, we can use number of moles. Now if we're solving for Kp, we probably want to use the partial pressures. If we're solving for Kc, we probably want to use our concentrations. If we have moles, we are free to use them, but we have to remember in the expression for Kc, we don't need moles of reactants and products, we need concentrations. And so we have to be a little bit careful if we use moles to convert everything back to concentrations at the end. So let's go ahead then and use our pressures. So what was our change? We were going and using up the products and making reactants. And so remembering to keep track of the stoichiometric coefficients. Every time we use up 2 of these, we make 1 of these. So this is minus 2x, this is plus 1x. So at equilibrium, this is going to be 1 minus 2x, and this is going to be 1 plus x. And we do the same thing as before. We write down our expression for K. Now it's Kp, but same principles. Partial pressure of iodine squared over partial pressure of iodine molecules. And we're told this value, so let's plug it in. So this was basically 3.12 times 10 to the minus 3. And that's equal to the partial of iodine. That's 1 minus 2x, okay, squared, over the partial of iodine molecules, that's 1 plus x. So unfortunately, we're solving this equation for x, and it's not a perfect square, so that means that we can't just square root both sides and be done very quickly. So we're going to have to cross multiply and solve a quadratic. Now, we've picked numbers here that are fairly easy to work with, so I don't think it's going to take quite so long as before. So we can go ahead and we can distribute out on the left-hand side, and we can go ahead and we can write the right-hand side out in full, and we can FOIL it out. So we've distributed the left-hand side, so now we should probably FOIL out the right-hand side. And we can collect terms, and so that's 1 minus 4x plus 4x squared. And the left-hand side, we've got terms here, 3 times 10 to the minus 3 and 3 times 10 to the minus 3 x's. So it's looking like a quadratic right now, so we just need to get all the x's and x squareds and numbers on one side and set the right-hand side to 0, and we can do that fairly quickly. And it looks like that, and then we've got a quadratic we can solve for. So again, we've got minus b, so that's minus minus, so that's plus 4.003. So that's our b, that's our a, and that's our c. Plus or minus root b squared, so that's minus 4.003 squared minus 4 times a, so that's 4 times by c, 0.997. Square rooting all of that, and that's over 2a, 2 times by 4. So we can solve for x, and if we do that, it looks like this. So again, all quadratics are going to have two solutions. Now, hopefully one of these is impossible, and the other one is physically possible, and we can keep it. And let's have a look back at the bottom line of our ice chart. We know that the partial pressure of iodine atoms at equilibrium was equal to 1 minus 2x. And we can see that if we pick this for our value of x, when we double it, it'll give us something like 1.068. And if we subtract that away from 1, we'll get a negative pressure. So again, we know that this one must be our physically reasonable one. And so if we take 1 minus twice that value, we get 0.066. And those are pressures, and so we need to put back our atmospheres. What was the partial pressure of iodine molecules at equilibrium? That was equal to 1 plus x, and so that's 1.467, again, atmospheres. So there we've solved. Now, the last step's optional, but I would probably go ahead and advise you to do it anyway. How do we know we got it right? Well, we can substitute back in, and there'll be some round-off error because I've not been very careful in this problem. And we know that it's supposed to equal 3.12 times 10 to the minus 3. So if we go ahead and we check, partial of iodine atoms, 0.066, we're squaring that, dividing by the partial of iodine molecules, 1.467, and if we calculate that, we get 2.97 times 10 to the minus 3. So I would say, yeah, they're within 10%. So I would say close enough for government work. So probably we've calculated things correctly. Cool, huh?